可以，没有问题。
好的。
Hello， 于老师早。
哎，晚上好。
那个就是我们前2天刚好去那个新竹做那个 A 世代计划的报告，所以那个因为我们之后可能还会有一个就是必须要比较具体的 demo， 那个部分可能那个台大吴宇老师会再找您做一些 detail 的讨论。
对，吴老师说他那个1月份会来美国访问。
哦，对，他可能会带那个我们台大的几个学弟，如果有空的话。
对。
好啊，谢谢于老师。
没问题。
那我想这个晚上的这个时间差不多，我们是不是就请于老师再帮我们做这个第4个部分，有关这个就从我们之前的 in-memory computing 现在到 3D 的部分，再做一些 detail 的介绍，谢谢。
Okay. So thank you. So let's get started for this week's lecture. So this week we're going to discuss 3D IC, 3D integration for the future circuit design, and we will leverage the in-memory computing and the emerging device technologies we covered in the last few lectures, and also we are going to use our new SIM as the major tool to evaluate the 3D IC's performance, power, and area. So let's get started for this week. So here, this is the outline for today's presentation. Firstly, I will discuss the monolithic 3D integration. And this relies on the backend of the NAND BEOL active device technologies. So this means we are going to sequentially integrate those devices on top of the CMOS into the interconnect levels. And then for the rest of the presentation, I will talk about the mostly heterogeneous integration. And that means we are going to stack multiple dies on top of each other with the advanced packaging technique. So here first I will discuss a 3D physical design with hybrid technology nodes. For example, if RRAM is designed at 40 nanometer process, as we taped out with TSMC, and then the CMOS could be at more advanced node. So in this example, we're going to show 16 nanometer FinFET process. And then the heterogeneous 2.5D and 3D integration really will take off as the industry is embracing this technology. So here we're going to show 3 applications for the 2.5D 3D integration. The first one is to design a near pixel compute accelerator with CMOS image sensor. And this is useful for autonomous driving and kind of application. And then we will talk about the very hot topic, the large language model acceleration. So here, this is to utilize the chiplet with multiple 3D cube to do this very large language model acceleration. And finally, we will talk about some new applications towards bioinformatics. This is to do the hyperdimensional computing with the 3D NAND, because here the bioinformatics will have a lot of data. For example, in the genome sequence, we are going to search the database with like gigabyte and terabyte genome sequence, and then those sequences will be stored in 3D NAND. So we're going to do the hyperdimensional computing with the 3D NAND. So those are new applications for the 3D integration. Okay, so then let's first look at the landscape for the 2.5D and 3D integration. There are many techniques, but let's take a look on the technological foundations for the 3D IC. So I would say here, if you look at a schematic showing the cross section side view of the chips. So here, first we have the face to back stacking with the TSV. TSV, is a through silicon via. So here we have multiple chips, and then they stack vertically, face to back. Then, in order for us to communicate through the chips down to the bottom, which is typically the substrate, like interposer or PCB, then we need to have this through silicon via TSV to go through the backside of the silicon. And so here, those chips, you see that actually facing down. So then the backside of the silicon, which is typically after the thinning, will still have like tens of micrometer thick. So you have to go through that silicon using this copper wire. And then this would be used for delivering the power from the substrate to the top dice. And also this could be used for the data communication, like signaling and clocking between the chips. So this is a face-to-back 3D IC stacking. And then actually this has been used commercially for some of the products today. For example, HBM, high bandwidth memory, is a good example for the DRAM. For this GPU, DRAM typically is HBM. So HBM rely on like 4 DRAM dice or 8. Even today, I think the most advanced HBM has 16 DRAM dice stacked in this way. And so then those chips will be a DRAM die, and then this will feature the high bandwidth, because here we have multiple connections between the DRAM's I/O. So we would have a wide I/O. So here then the DRAM's TSV and bump, this bump will be micro bump. So those will be the foundation for today's HBM. And then a different design with this heterogeneous 3D ICs to have the face-to-face bonding. So here we can have the chip, bottom chip facing up, top chip facing down. So then this is like face-to-face bonding. And then beyond the micro bump, there's a new trend to use this direct or hybrid bonding, which could have smaller feature size for those bonding pad. So here this could be a more advanced, and the industry has also enabled this kind of technologies. For example, TSMC has the SOIC technology, and the Intel has its Foveros technology. So this could be very useful. For example, AMD's 3DV cache, where you can stack multiple SRAM dice for the last level cache for the high-end processor. So you can use this hybrid bonding technique for the vertical stacked cache system. So here then, let's look at the 2.5D. So 2.5D is, multiple dice placed horizontally on the same plane, but there will be an interposer, which is typically silicon, for the communication between the dice horizontally, and also there will be TSV through this silicon interposer down to the bottom to communicate with the PCB or get the power from the PCB. So this could be the chipnet integration. So each chip will be a chipnet, and then on the interposer, there will be interconnects. And sometimes you could have active interposer where you have active circuitry on the interposer as well. And today's 2.5D IC, a good example is the GPU, right? As I said earlier, for example, here the chip 1 could be actually a stack of those multiple DRAM dice. Then let's say this chip 1 stack is a HBM. And then chip 2 is the GPU. So then the GPU, NVIDIA's GPU is talking with the HBM through the silicon interposer. So this is a good example. And finally, let's look at the monolithic 3D IC. So this is not commercialized yet, I would say. This is still under the research. And in this case, we are going to have, let's say, a CMOS substrate, active layer 1 with the transistors. This will be the silicon transistor. And then we are going to, this is facing down, by the way, this is facing down. So then we have the top interconnect down to here. So then those will be interconnect layer 2, layer 3. Of course, this will not be like your metal 1, metal 2. Let's say layer 2 is a group of maybe in metal 6 to metal 8. Layer 3 is a group of interconnect from metal 12 to metal 14. Then on those metal layers, we could have active devices, that means transistors, on those layers to enable new functionality. So this is sequentially processed on the CMOS. There's no like bonding. This is sequentially processed. And then this is called monolithic 3D. And then those layer 2, layer 3 is called back-end of the LAN integration. So this is a landscape for the 2.5D and 3D integration today from the technology perspective. And then here, one big motivation is to have this interconnect pitch scaling for the 3D IC. This is a figure from IMEC. And today's commercial product mostly have the package on packaging stacking and multi-die packaging technique. So those still will have a very large feature size in terms of the pad pitch. So it's generally like 100 micrometer in that dimension. If we want to go into the, so this is called system in package. And here, if we want to have the more advanced integration. So here, for example, if we have the micro bump and the hybrid bonding, then this could enable the pitch scaling. So the micro bump is a smaller version of the bump. So between those dies, you have the soldering of the bump. And then if you shrink the bump to be the tens of micrometers per scale, for example, 30 micrometer scale, it's called micro bump. And this micro bump would enable more bonding between the dies. So the micro bump, as I said earlier, is the basis for the HBM stacking. And then hybrid bonding will get rid of the bump, have the copper to copper direct interface. So then this hybrid bonding pitch today is roughly, let's say 6, 7, 8 micrometer in that dimension. So this is smaller than micro bump. And both micro bump and hybrid bonding have been commercially available. For example, TSMC has CoWoS technology, which mostly is on the micro bump. And the TSMC has also an emerging technology called SOIC. This is based on the hybrid bonding. And then here, the eventual goal is to have the wafer to wafer hybrid bonding, because today is mostly die to wafer bonding or die to die bonding. So wafer to wafer will be more challenging because you have to ensure the alignment of the entire wafer. So this could approach potentially 1 micrometer scale in terms of the bonding pitch. And IMEC has demonstrated some nano TSV or micro, even nano TSV, where the TSV's dimension is 500 nanometer or so. So this is approaching the limit of this bonding. And then beyond that, then we have to do this monolithic 3D integration, where you process the wafer sequentially on the back of the LAN using the back of the LAN interconnect processes. So this could have the interconnect pitch like hundreds of nanometer for the metal wire pitch. So this is like the back of the LAN stacking. And ultimately, then this 3D IC could be based on the front-end 3D transistor. So then this could be the future 1 nanometer low CFET complementary field effect transistor stacking. So this is front of the line 3D transistor. So we are not going to discuss this one in more details today because this is on the advanced logic process. So roughly this is a landscape for the pitch scaling. And just one slide on the 3D CFET, since we are not going to discuss this in more details. So if you look at the recent industry roadmap, so for 1 nanometer and beyond, they're going to switch to this CFET, where they're going to stack the NMOS on top of PMOS. So NMOS and PMOS each will be the nanosheet based gate-all-around transistor. And then they're going to have this NMOS stacked on top of PMOS. Therefore, the inverter could be like a 3D vertical inverter. And in this year's IEDM, which is coming next week, both Intel and TSMC demonstrated the CFET feasibility for both inverter and other logic gates. So here, this is the TEM under the microscope to show the side view of Intel's 3D transistor. So here the PMOS is on the silicon germanium and MOS is the silicon. So this will be the nanosheet. And then if you have the 3D CFET, you can do the 3D SRAM design, where you can fold some of the transistors on top of each other. Therefore, this is like a preliminary layout for the design. I believe this is a traditional, the FinFET based design, or even nanosheet based design layout. And then on the height, we are going to have 8 fin pitch. And then here, if you fold into 3D, then you will save half of the area. So this is a great way to improve the density for future SRAM technology. Okay, so this is on front-end line silicon processing. We're not going to spend more time on this one. This is still the hot topic from the industry for their most advanced technology node. So what we are going to discuss more today is on the back end of the line. That means on top of the interconnect. There are opportunities and space available for innovation, where universities could also contribute to this domain, because here on the interconnect level, the dimensions are more relaxed and the pitch will be larger. So even universities could demonstrate something useful. Unlike the 3D CFET, which is like 1 nanometer load, then universities could not do too much for the demonstration there because it's an industry's play. Of course, university may do some modeling simulation, but experimentally, there's no way for universities to work on anything useful for the 1 nanometer load. So anyway, here for the back-end line, the idea is, as I said, so here you still have your front-end line silicon with the substrate, and then on the back-end line, on top of the interconnect, we have transistors as active device. But those transistors need to be very low temperature fabricated. So here the back-end line has a stringent thermal budget less than 400 degrees Celsius. The reason is that when you do the metallization on the back-end line, you have to limit the processing temperature less than 400 C to avoid the damage to the front-end line and transistor performance, because those metals typical melting temperature is like around 400 degrees C. If you have temperature higher than that, then your previously fabricated lower metals and the front end of a transistor will have damage. So you have to limit the processing temperature to be less than 400 C. So this is a critical challenge if this transistor is based on silicon. For the front end line silicon processing, you need 1000 degrees C. For example, for the source and drain dopant activation. So you need 1000 degrees C processing. Therefore, single crystalline silicon is not available as a backend of NAND. That motivates us to look at alternative channel material other than silicon for those backend of NAND transistor. And we'll talk about that channel material options in next few slides. But here are the applications we can think of for the backend of NAND transistor. First, you can still use it for digital logic operation. So for example, you can partition the CMOS circuit between the front-end LAN and back-end LAN. For example, front-end LAN, you still have the silicon. Back-end LAN, you have the other material-based NMOS. So here you have 3D stacked CMOS logic. But more interestingly, back-end LAN, you can have memory, a lot of memory there. So here the memory we have talked about, for example, 1T1R or the 1T1C FERAM, or the 2T gain cell EDRAM, or the 1T ferroelectric transistor FEFET. So those transistors you see all have the T transistor there. In today's front-end line integration, those T is a silicon transistor for 1T1R. For example, TSMC's 1T1R for the R1 process, that T is the front-end of NAND T transistor. But if you can relocate those T at the back-end of NAND, because R1 cell is back-end of NAND anyway. And if you can put the transistor, this access transistor, also back-end of NAND, then you can have the memory fully on top. So this is a very attractive feature. And also there are new applications enabled by this back-end of NAND transistor. For example, we have been pioneering this in this power transistor design with the back-end of NAND process. So you can have the integrated voltage regulator on the back-end of NAND. So for the DC-DC voltage conversion. And this is useful when you talk about the heterogeneous computing, where you have different VDD for different chips. Then you can convert the voltage on the die. Because today's power conversion mostly happens off chip. You have a separate power management chip. And then here, if you can have the power conversion, voltage conversion on chip, then you can improve the efficiency in terms of the power delivery. So there are opportunities using the back-end of NAND transistor for the power delivery as well, active power delivery. And finally, because back-end of NAND, you have a lot of metal interconnects. And if we can make those interconnects reconfigurable, then you can dynamically control the data flow. So for example, you can have the routers, routing switch on the back-end of NAND. And this could be very useful for FPGA design, because FPGA has a lot of router and also even lookup table. So there are many SRAM configuration memory for the routing and a lookup table. So if you can put those SRAM or even get rid of the SRAM and use the interconnect, which can be modulated in terms of the signal routing, then you can enable this SRAM-less routing configuration for the interconnect. So those are many opportunities we are interested in, and I will showcase some of those examples in the next few slides. First of all, for the channel material, as I said, won't be silicon for the backend of NAND. So there are different choices, primarily 3 classes of material. So first is still silicon, but this won't be your front of NAND crystalline silicon. If you do backend of NAND, mostly polysilicon, polycrystalline silicon, where you don't need a high temperature annealing. And so also there are some approaches to use laser to recrystallize the silicon. So I think both CENIT and TSRI in Taiwan also have been working on this laser recrystallized silicon. So here, the mobility of those polysilicon or recrystallized silicon is roughly 20 to 50 centimeter square per volt per second. which is decent. You know, front-end non-silicon is more than 100 mobility. So here the mobility is lower, but more a greater challenge here is the uniformity, especially the polysilicon and the recrystallized silicon, because it's not uniform across the wafer. So then this will suffer more from the uniformity challenge if we stay with the polycrystalline or recrystallized silicon. And then recently, I think the research community has more interest in oxide semiconductors. So here are those oxide as shown in this table, this graph. So this is mobility versus the band gap of those oxide material. So this is also called wide band gap semiconductor, because their band gap is larger than silicon. You know, silicon is about 1.1, and here the single crystalline silicon you see here is somewhere here, and then the wide band gap oxide semiconductors could also have some decent mobility, especially for electrons for NMOS design. So here the industry is pretty interested in those candidates, like indium oxide, gallium oxide, IGZO, this is indium gallium zinc oxide, IWO indium tungsten oxide, ITO indium tin oxide. So mostly you see that we have indium in the oxide. So that's an indium oxide family. This could be useful because here for the oxide semiconductors, you don't need high temperature processing and deposit at really low temperature, even close to room temperature, if you do the PVD sputter. So even you do the ALD, then it's like 200 degrees Celsius. So this is very attractive, and many research groups and industry is working on the oxide semiconductor-based platinum line transistor. For example, this year, if you put IEDM, then IMEC is going to publish a paper using the IGZO as the access transistor for the DRAM. And so here, the advantage for this oxide semiconductor material is that the band gap is higher than silicon. That means the leakage current, the off current, is much lower than silicon. So you can have ultra low leakage current from those transistors, which is good for DRAM, because DRAM, you know, the access transistor needs to be super low leakage. And then this oxide semiconductor-based transistor could naturally serve that purpose. However, here for the oxide semiconductor-based device, there's one challenge. That is, there's no P-type oxide available. So the best P-type oxide demonstrated today is the copper oxide. Copper oxide, the best mobility is just 1 centimeter square per volt per second. So you see it's much lower than the NMOS. If you do a inverter design, you have to size the PMOS 20 times larger than NMOS to have a matched CMOS circuitry. So the PMOS is a big challenge for the oxide semiconductors. So basically, there is no holes available in the P-type oxide. So here in this table, you see many circles with the holes, but those are prediction by theoretical calculation. So here there's a star on those material. So this is from the AP initial calculation, predict those oxides may have good mobility with holes. However, those are not fabricated yet, and it's very difficult. You see those compounds are very complex material system. So it's very difficult to demonstrate for the P-type today. And finally, there is interest in 2D material, and mostly people have demonstrated MOS2 for N-type and WSE2 for P-type. So the 2D materials have reasonable mobility, but 2D material have more challenging integration challenges in their gate stack and contact. So the interface between the gate dielectric to the 2D material and also the metal contact source and drain to the 2D material will introduce a lot of parasitics defects. Therefore, the overall transistor performance will be limited by those interfaces, even though the channel by itself could be high performance, but the overall 2D material-based transistor may not show great performance. And also 2D materials, are more far away from CMOS fabrication in terms of the compatibility of the material system. So here I would say the industry is betting in these oxide semiconductors because this is closest to the CMOS processing, and it has some good attributes. The only challenge here is the p-type is missing. Okay, so here then I show some examples for this oxide semiconductor background line transistor. So here this is example from my collaborator, Professor Sumandata's map. This has been published in VLSI and IEDM in the past 2 or 3 years. So here the channel, this is the Indian tungsten oxide, and then here we have a double gate with hafnium oxide gate dielectric, and then we have the platinum as the gate metal and also source and drain metal. So here, then this is the IDVG of the transistor characteristic for this IWO transistor. You see a pretty decent substantial slope, and then here the on-off ratio is also large at 10 to the power 9 magnitude, and then the on current at 2.5 volts is like 400 microamp per micrometer, so it's also pretty large. And this is typically compatible or even better than I/O transistor of the silicon at the 2.5 volts. However, here the challenge is at the logic VDD, for example, 1 volt. If you look at 1 volt, here then the current is much less. So at 1 volt, the current drive density is 3 times or 4 times than silicon NMOS logic transistor at similar voltage. This is because the mobility of this channel is only 20 or 25, which is 4 times lower than NMOS N-type silicon, which is 100. So here, in order to increase the current density, what we can do is to stack multiple nanosheets with IWO. So here it has not been demonstrated yet, but from the TCAD simulation, we could do that potentially to increase the drive density of this IWO transistor. So if we have this IWO transistor, what can we do? For example, here we have proposed to design the I/O transistor using this IWO NMOS, and then have a PMOS silicon on the bottom, so which could have comparable performance as a 2D pure CMOS level shifter, but we can save the area. And so here, this is typically the level shifter circuit, where you can convert the voltage from the low voltage domain like 1 volt to the high voltage domain like 3 volts. This is useful for many of the memory circuits. For example, R1 FFET, because their programming voltage is like 3 volts. So we have to boost the voltage on chip. So we have a lot of level shifter on those memory circuits. So here, the advantage is that if we do here, for example, the NMOS, replace all the NMOS with IWO transistor, and the PMOS still stay on the silicon, then here you see the improvements of the layout. So here, if you do the 2-dimensional CMOS design, then with I/O transistor, because you have to sustain 3 volts, then this is NMOS, this is PMOS for these circuits. And then if you do the 3D design, first of all, the NMOS transistor here, the gate length could be smaller than the silicon NMOS. Because if you look at the I/O transistor silicon with NMOS, the L is like 200 nanometer or 300 nanometer. even for advanced like 28 nanometer or 16 nanometer technology node. The reason is that you have to sustain 3 volts, so then the IO transistor size is large. But here for the IWO transistor, you can use shorter channel, like 50 nanometer, could also sustain 3 volts. So for 3 volts silicon, you have to have 300 nanometer. And here for the IWO, you only need 50 nanometer for 3 volts. The reason is that the IWO, is a wide band gap oxide. The band gap is like 3 electron volts compared to the silicon's 1 electron volt. So naturally, it could sustain larger voltage to avoid breakdown. So here, then you can shrink the horizontal dimension, and for the NMOS area, because NMOS dominates in this circuits. And then for the 3D IC design, you can fold this NMOS part on top of the PMOS, because here this NMOS is IWO, which you could fabricate it on top of the PMOS silicons interconnect. So first shrink the horizontal dimension, and then along the dash line, you fold this part on top of the PMOS. So you can greatly save the area for the IO transistor level shifter design. So here we have done the simulation, and in terms of the waveform to be driven from the level shifter, and here seems that the IWO could match the CMOS design with a reasonable delay. So here then we mentioned this kind of folded design. And for example, still you have PMOS silicon on the substrate, and the NMOS is on top. So like this one. So this is like 3D partitioned CMOS design. Previously, two-dimensional case, you can NMOS and PMOS are side by side. Now the 3D design NMOS and PMOS, NMOS is on top of PMOS. So we want to also build a design flow for this 3D partitioned CMOS technology. So here we want to use the commercial EDA flow, but here we have to first develop the 3D PDK because it's design kit. So we created the standard cell library with the 3D based CMOS logic gates, like the inverter, low gate, NAND gate, XOR gate, and so on. So we have this library with the left file, lead file, and make the a library available. And then we can use the commercial EDA design flow, from the behavior description to the RTL, and then to the synthesis, and then placement and routes. So we can create the entire physical layout. So here are just some examples for different circuitry, like AES, the encryption circuitry, and a simple RISC-V core. So if you do the 2D CMOS, this is how it look like. And then if you do the 3D partition design, then you are going to shrink the die size roughly 50%, because you have the PMOS, NMOS on top of PMOS. So here are just some exercise to show that you can still rely on the commercial EDA tool flow if you have the 3D PDK and standard cell library available. So here we are going to show another application, which is the memory access. So here the 2T GaN cell is embedded DRAM where you have a read transistor and write transistor. You could place both of those transistors on the top of the CMOS front end peripheral circuits, like your decoders and SAM and so on. So you can have the memory on top of the CMOS. So here, then this IWO transistor, again, as I said, the leakage is pretty low. So the measured off current is like 1 femtoamp per micrometer. This is like a DRAM access transistor leakage. The logic transistor is about 1 nanoamp per micrometer. So this is 1 femtoamp per micrometer. So this is pretty good. So with this two transistors, both are IWO. We have worked with Professor Simon Data's team. And their team has demonstrated the 2T gain cell ED-RAN and cell, and with the retention less larger than seconds at the room temperature, or even at elevated temperature, still like millisecond retention. So this is good for the embedded DRAM application, where you can have a lot of DRAM cell on top of the CMOS. And also we mentioned that the background line FE FET, because you still have the channel for the FE FET. And then unlike the front end of the line, you have silicon channel. Here you can have the IWO oxide as a channel. And then you still have the ferrogate dielectric coupling zirconium oxide. Then you can have the background line FE FET. So this is the hysteresis in the IDVG of the FE FET. You have this in the memory window. And then you can cycle this device for more than 10 to the power 10 cycles. So if you recall this endurance data for FE FET, this 10 to the power 10 cycle, or actually the 10 to the power 11 cycle, is much higher than the global foundry, for example, the front on the line silicon FE FET, where the endurance is typically 10 to the power 5 or 10 to the power 6. So here is 10 to the power 10 or 10 to the power 11. So it's like 1 million times better. So why is that? This is because here if you use oxide as a channel, so between the oxide channel and then the coupling zirconium oxide ferroelectric gate, there's no interfacial layer. It's both are oxide, right? So the interface is pretty good. So you do not have those defects, traps to degrade the endurance. If you recall, we discussed about the silicon FE FET. There is an interfacial layer. The silicon, to transition from silicon to the coupling zirconium oxide, there's the interfacial silicon dioxide. So that silicon dioxide will create a lot of troubles for the endurance. So here, naturally, if you do the background line FE FET, the endurance will be improved because the oxide channel's advantage over the silicon. And also here, the retention is pretty decent. So you can have the FE FET fully background line as well. So here, another application. This is what we recently discovered. So we can do the fine-grained power management on the background line using the integrated voltage regulator. So here, for example, we have the switch cap-based DC-DC converter. So we can convert the input and output voltage levels like 2-to-1, 3-to-1, 3-to-2 ratio. So here, then we can modulate the VDD dynamically if we can have the IWO transistor on top of the interconnects. So for some blocks, we can have the VDD, for example, 1 volt. Some block, we can have the VDD 0.8 volts. So we can have the fine-grained power management using the active power delivery network. You know, today's power delivery network, like your VDD and VSS, is purely passive on chip. So you just deliver those VDD and VSS, make sure the IR drop is minimal. But the voltage conversion is done off chip. So on the chip, you will only have one voltage domain in most cases. And if you want to change the voltage domain, you have to rely on the off-chip power management module. So here we can have this DC-DC converter on top of the logic. Then we can control a block of the logic with its individual VDD. So this could be useful for the DVFS. It's fine-grained DVFS, dynamic voltage frequency scaling. So for example, in the neural network propagation, then, you know, depending on the workloads, you can dynamically change certain tiles or certain blocks of the circuits to be in the high performance mode, where you have high VDD, or in the standby idle mode where you have low VDD. So then, depending on the data flow, you can dynamically change the VDD and then the frequency of those blocks, because now you can have the block level voltage control. So this is enabled by the back-of-line power transistor. And then here, one tricky part is that in the conventional DC-DC converter, you have PMOS transistor as a high side switch. But as I said, there's no PMOS available for the offset channel. So here we have to use the depletion mode of the offset channel. That means we have the MOS, both MOS, but then for the high side switch, we're going to use the negative VTH of the NMOS to mimic the PMOS. Of course, it's not ideal, but at least functionally, we can demonstrate it with the converted voltage. So this is possible because here at the IWO channel, the VTH could be tuned by the fabrication process by controlling the oxygen vacancy concentration or density in the channel. So the VTH is tunable. So we can make it high side switch and low side switch. And also here for the interconnect, we talk about the reconfigurable interconnect. So the idea is that for the, for example, 6 transistor switch, routing switch, so it typically, in the conventional design, will be a cascade transistor controlled by the SRAM. So if SRAM stores 1, then you allow this pass transistor to turn on, so the signal can pass, for example, from this node to here. But if the SRAM stores 0, then this will be blocked. So we can do this by FEFET, back-of-line FEFET, as we showed earlier. So the FEFET, you have the different VTH. You can program the VTH to be high. Therefore, then you can block the signal. If you program the VTH to be low, then you can allow the signal to pass. So it's essentially you can program the FEFET in different VTH states. Then you can have a long volatile version of the configuration of the routing switch. Therefore, this could be very useful for the FPGA and other reconfigurable architecture design. Because now you don't need the SRAM, 6 transistor SRAM as a routing switch. And then you can have those routers fully on top of the interconnects. And here with Professor Sumendata's team, we have demonstrated the 6 transistor router with FEFET. And here we can allow the signal to pass with like 250 picosecond delay, pretty decent. And then we have shown the reconfiguration and measured the cutoff frequency and for the signal routing up to like 11 gigahertz. So you can pass those signal pretty fast through this FEFET channel in the on state. Of course, we can block it if we do not allow the signal to pass. And another advantage is that this is non-volatile memory. That means this routing configuration could be stored during the power off state. So this could be very useful because if you think about today's FPGA, when you use FPGA, first time when you power on the FPGA, you have to write in the configuration bits, right? So you have to do the scan in of the SRAM configuration state from your software, like your Xilinx, whatever software. You have to do the synthesize and then load in the configuration bits sequentially to the FPGA to configure the data flow and configure the logic state. But here, this is the non-volatile, then the configuration is stored on the FEFET. So once you power up the chip, then your logic is still there. So this is very useful compared to the SRAM-based configuration. You have to reboot and then do the reloading. So it will take typically seconds to finish that loading. Okay, so here to summarize, back-of-line transistor would be very useful in many of those applications as I discussed earlier. So there are many research needs still. This is not perfect. We have missing the p-type oxide with high mobility. So this could be a major roadblock for many designs, because still the CMOS logic is the best in terms of the functionality and then the leakage power. So here we need to further increase the drive current density for the oxide semiconductor, because the mobility is still not as high as the silicon. And also has a big challenge on the VTH stability under stress. So one challenge of the oxide semiconductor is that the threshold voltage is not very stable. It may change over time. So then we have to somehow encapsulate the oxide semiconductor and make it stable. So this is still to be verified. And finally, we have to characterize, the noise reliability and variability with more statistical data. So here, then there are many research opportunities as well. For example, we have to do the code design, DTCO, and the PDK development for the back-end run transistor, and also adapt the EDA to design flow. And then maybe we can also enable some new applications like the split manufacturing for hardware security. And finally, we have to address the thermal issue in the 3D IC, because as you stack more and more active components to the backend, then those backend will become, hotspot. Then we have to deal with the thermal or heat dissipation. So this will be the research needs and opportunities for futures 3D monolithic 3D IC design. This is all monolithic because we built those transistors on the interconnect level using sequential process. All right, so then in the following of the presentation, I will talk about the heterogeneous design, which means we are going to have fabricated dies separately and then do the bonding. So first, then let's look at the physical design with hybrid technology loads. So here we have seen the RAM-based computing memory in one of the earlier lecture. And the challenge, if you recall, we have large ADC and also level shifter. And then also the ADC is large. So then we have to have the sharing between the ADC for different columns. Let's say 8 column share one. And ADC consume a lot of power. So that's why it's not very friendly in terms of the layout and also the power consumption for the RAM-based computing memory. Even we have designed and taped out with TSMC processes, the design is not very optimized. So proposed the solution for that is that here we can still design the RAM and with whatever technology available. Typically, older technology node, for example, TSMC 40. And then for the high voltage transistor, like a level shifter max, we can still stay with RAM because we need to have 3 volt operation anyway. But then for the other peripheral circuits like ADC, shift net, buffer, and other, clock and control, there's no high voltage involved. Then we can design that in more advanced node, like 2816 or even more advanced node. So this could be a heterogeneous partition between different technology nodes. And then we can have more space here for the ADC, because now the ADC is basically placed underneath the RAM array. Now we could have more space for the ADC. Potentially, you can have each column to be equipped with one ADC, so we do not have the ADC sharing problem anymore. So this is the hope for this 3D IC design. So here we have done the exercise to design a 2.4 megabit RAM computing memory tile. So this is a collaboration work between my group and Professor Sanqiulin's group, who is an expert in the 3D EDA flow. So still we use the commercial design tools like the Virtuoso and then the Innoverse tool for the synthesis. But we have to modify some of those technology files because we have different technology nodes. So we have to use 40 nanometer and then more advanced 16 or 28 nanometer. Because the best we can do is 16 because we only have 16 nanometer PDK in our lab. But in principle, you can do more advanced technology load if you have the access. So here then we have to adopt this EDA flow. And here, let me show you what we designed. So here basically is a hierarchical computing memory accelerator, where on the subarray, we have the 128 by 128 ARM array. And then we have the peripheral circuits, like those level shifter, mux, ADC, and the encoder and shift and add. So this is like one subarray, and then we have the 4x4 subarray with for 1 PE with the control circuits and input and output buffer. And then on top we have 3x3 PE for 1 tile. Then we have the accumulations and other tree and buffers between those PEs. So it's a complete design. And then here we're going to partition this into 2 tiers. So here, this is the final synthesized physical layout. Of course, we have a baseline, which is 14 nanometer homogeneous design. So here we'll show the physical layout for the 3 levels in the hierarchy. So this is the one subarray, and one subarray, will become a portion of this 1 PE, and 1 PE will become a portion of this 1 tile. So here, let's look at just the subarray, so it will be more clear. So here you see the R1 is 128, it's like this size. And then we have the mux to share the ADC, and the level shifter to convert the voltage domain. And then this is the digital control and the post-processing. So you see the area is not very efficient, right? So R1 only occupies this space and not of peripheral circuits. And we can partition those peripheral circuits into 2 tiers, as I said earlier. For the high voltage transistor-based module with the mux and level shifter, we can stay with 40. So here you see after partition, this top tier is 40 nanometer process. We still have R1 and a level shifter and mux. So this is PE level. So if you look at one subarray, so it will be like this. This is one subarray, like this one subarray. But here we only have the R1 and mux here and the level shifter here. So under this R1 tier, then we have the logic. So here the ADC and the digital control will become here. So those will be almost a balanced area. Because here for this digital and ADC, we're going to use more advanced node, for example, 16 nanometer to design those logic gates. And even ADC mix mode circuits, we can use the 16 nanometer because the voltage to sense will be not high voltage. So this will be partitioned and matched. So we can have a heterogeneous 2 dies. And of course, between those 2 dies, there will be many interconnects. So we have to so for this to be feasible in fabrication, so we have to assume very advanced hybrid bonding with like a few micrometer pitch, or even close to 1 micrometer pitch to enable the high density interconnect between those 2 dies. So here is the PBA. If we run the simulation post layout, then here you see that for the 2-dimensional 2D baseline, everything is on 14 nanometer process. And then this is the statistics of the total die size, total gate count, ADC, number of ADC, and total area, and then the total power, and then converted kiloops per watt. So here, if we look at the final design, let's say here this one, if we partition, let's say 14 nanometer top tier, 16 nanometer bottom tier, and first of all, we can shrink the size of the chip to be 1.7 by 1.7, so roughly 50% decrease of the total footprint. And then we can add more ADCs because now we have more space in the bottom tier, so we have more ADCs. Then we do not have the ADC sharing anymore. So then here we are going to have better throughput because we don't have the ADC sharing. This could boost the energy efficiency, and also with more advanced node technology. So you see that the energy efficiency will be like 4 or 5 times better than the 2D baseline. So this is pretty good. But of course, here one thing you need to notice is this one, the MIV count. This is the bonding pad you need between the two dies. This is number of pads. So if you convert this, let's say the number of pads divided by the chip area, this gives you the bonding density. So you need roughly 100,000, 100K number of pads per millimeter square. So if you convert this to the size of the pitch or the pad, it's roughly 3 by 3 micrometer square per pad. So this means you have to use very advanced bonding, like this hybrid bonding, or maybe hybrid bonding in future generations to enable this design, because this is still beyond the industry's capability today. And then here we also have done the thermal analysis for the 3D IC. So here we have used the ANSYS simulation tool to evaluate the temperature between those two dies, depending on the power density from the two dies. Actually, then the temperature increase is moderate, only 10 degrees C higher temperature than the 2D design. The reason is that here the computing memory chip itself, the power density is pretty low. So here the power density is less than 0.1 millimeter square. Of course, if those two dies has higher power density, for example, typically GPU is running, at this density, like 1 watt per millimeter square. Use GPU die, if you recall, like NVIDIA GPU, hundreds of millimeter square in the die size, and the watt is a few hundred watts. So it's roughly 1 watt per millimeter square. If you run those kind of large scale system, and if you stack in the 3D, then your temperature will be very high. Like if your die size is 100 millimeter square, and if you stack with such high power density, your temperature will easily be more than 100 degrees Celsius, which is not very feasible. So here, this is good for this low power chip. The temperature increase is very moderate. Okay, then next I go through 3 new applications. And so far this is still like a logic memory, but then there are many new opportunities. Let's say more than the more. There are new technologies available for 3D integration. So one of that is the CMOS image sensor. So CMOS image sensor, is a camera, right? Under the camera today is all CMOS image sensor. So CMOS image sensor actually is very, a good candidate to embed the intelligence to the CMOS image sensor. So here we have one project to look at the autonomous driving, and then we have designed the 3D IC for the front-end processing and also the back-end processing for this smart camera. So here the idea is to reduce the data volume when we take the high-resolution images, actually video during the driving. Then we are going to identify those objects and track those objects. But there are many pixels, not very useful, because the background, like the blue sky, and then other background, not very useful. We don't need to transfer those data from the image sensor to the backend line accelerator. So the data volume, if we can reduce the data volume, then we can save the system energy. So here the idea is to filter out those redundant pixels and only pass the useful pixels for the accelerator to process, to do the object tracking and detection. So here then we have to do something at the front of the line here. the front-end processing means under the camera, we need to do something. So the idea is to first filter the frames, because this is a video for the streaming and images. So we have to identify which frame is useful, and then we can drop the redundant frames. For example, if the car is sitting in front of or driving slowly, or even stop at the traffic lights, then across many frames, the images are, changing very minimal. So you don't need to, pass all those redundant frames to the backend. So we want to have a neural network here to identify which frames are useful. If you are driving fast, then probably you have to, pass more frames to the backend for the processing. So anyway, here we want to have a lightweight neural network directly integrated with the CMOS image sensor to identify which frame is useful and then pass the useful frame. And also within the frame, we only want to pass the object that is of interest to the backend for the tracking. So here, to summarize, what we want to design is a CMOS image sensor plus a temporal frame filtering accelerator, we call TFF. And then for the backend, we want to do the object detection and tracking because we have those objects of interest. Then we want to track that along the video. So we are going to design a vision transformer model to do that job. So here, let's look at the front-end temporal frame filtering network. So here, this is the motivation. We want to reduce the data movement from the CMOS image sensor to the host processor by rejecting redundant frames. So this is a very lightweight neural network, only 3 layers, and each layer is kind of small. But here we can filter out which frame is useful. And then this is tested on the BDD 100K dataset, which is a standard dataset for the autonomous driving. And so it's a high resolution image taken at 30 frames per second. So this is real time image or video. So then to process, or let's say to integrate the accelerator. So here we're going to use the face-to-face bonding. And we assume 3 micrometer pitch for the bonding pad. So here, this is top die is a CMOS image sensor. So for CMOS image sensor, is typically back illuminated. That means the back side of the silicon, we will have the photodiode for different, the wavelengths. And so you have the RGB colorful information. And then you will have the transistors to digitize those, the pixel. After you have the photodiode, you will convert the light intensity to the current level. And then through the transistor, you can digitize the current level to the, let's say, a current, and then you convert that to the time pulse width, and then have the time counter to count the time window. Therefore, you can get the pixel value. So you have some circuitry here, a transistor, pixel transistor to do this job. And after that, then you will have ADC to digitize that. And then, because this is a streaming condition, you need the buffer memory to store at least one previous frame. And because in this network, we are going to take the frame difference to look at whether we should keep or drop the current frame. We have to compare with the previous frame. So you have to have some buffer memory to store that. So here, since we don't store it for a long time, we can use this 2T gain cell, as we discussed earlier, for the embedded DRAM. So we can use that as buffer memory. So this is already bottom die. So here we have the interface between those two dies. So here on the bottom die, we have some logic circuitry to do the near pixel compute for the 3 layers neural network, as we discussed earlier. So here, this is the architecture for that near pixel compute architecture. So here, as I said, so the EDRAM-based buffer is going to store those images, or at least the 2 images, in the nearby frames. And then this will be loaded into the first layer. And then here we are using kind of a digital CIM scheme to do the multiply and accumulate. But we're not going to use SRAM for the digital CIM because here we don't need the data to store for a long time. This is streaming condition, so the images will come and go every 30 milliseconds. So we only need some logic gate that can hold the data for like 30 milliseconds. So we can use some specialized NOR gate to do that. And then after the multiplication and accumulation, then we have the adder tree, and then we can do the processing for 3 layers. And then finally, we will have the decision whether we're going to keep or drop this frame. So here are some more details in the circuit design. So for the pixel layer, this is the standard implementation for the pixel. This is pixel circuitry, photodiode, and then some pixel transistor. Basically, depending on the light density, you can have different photocurrents, and then you can have different voltage on the storage node. Therefore, you can have the comparator. And then you depending on the current, then you can have a different time window after you do this pulse width modulation. So then you can have the comparator to count the number of the time window. Therefore, you can have the pulse width modulated signal, and then later you have the ADC to. At the ADC is essentially time to voltage conversion. So you can have this output as the pixel value. So I'll skip the details. This is pretty standard implementation of the CMOS image sensor circuitry. So here one innovation is that, as I said, for the buffer memory. So typically after the ADC, then you will store those pixels into the register or store in the SRAM cache. And here we're going to use this 2T gain cell to temporarily hold the data for 33 milliseconds, at least the buffer for 1 frame. And then for the bottom near pixel digital SIM accelerator, as I said, this is typically like the SRAM-based DSIM. But here the only difference is that we don't use SRAM, use the NOR gate, where the input gate capacitance is sized up a little bit. So we can use that as a storage node because we only need to store the data for 33 milliseconds. So here then the MAC is happening here in this digital SIM. And then the input for the MAC operation, one input will be the pixel value stored from here, the EDRAM cells, and then the other input is the weight of the neural network. In this case, those weights are stored in SRAM because you have to maintain that for a long time. But the calculation result is also temporal. You only need to accumulate this MAC operation through the adder tree, and then after some shift and add and the ReLU function, then you can compute the activation of this neural network for 1 layer. So here, of course, if you look at the DSIM in the big part in the adder tree, and TSMC has published some designs to use some full adder tree, half adder tree to optimize this a little bit. And also we propose some sparsity of their adder tree. So if the input are all 0, we are not going to, because 0 multiplied by 0 is 0. Or let's say 0 plus 0 is 0. So we're not going to go through the adder. So if the input is 0, we're going to bypass that stage. So this could save some of the computation as well. So here then this is so we did, by the way, so we did the synthesis of the entire accelerator with this kind of architecture, and then this will be the results. And then we scaled to 22 nanometer load, and then this is the performance for 8-bit by 8-bit computation. And then compared to other near pixel compute applications, So here the design is purely digital, and then we can have the the best efficiency and the high computer density because of the 3D IC. So this is of course of simulation results compared to other near pixel in pixel processing schemes. Okay, so then let's look at the full system. We just cover the CMOS image sensor. So after we get the frames or the useful frames, after we get rid of the redundant frames, we still need to send those useful frames to the backend processor to detect the object and track the objects. So then the backend, what you can use, typically you can use FPGA to do that, or if you equip GPU for that, that's also fine. But this is very power hungry for GPU or even FPGA. So typically, what you will do is to have a CMOS image sensor and your backend backend FPGA or GPU. So here, this is example of FPGA. You have some interface with the 2.5D I/O links on the silicon interposer, and then the FPGA will be equipped with HBM or GPU equipped with HBM. So this is high-end FPGA. So then a lot of data transfer will happen between those interconnects. And also then the FPGA will be power hungry. So by the way, here, this is what we propose actually to have those front-end processor, let's say the CMOS image sensor, and back-end, the object detection and tracking and accelerator on the same silicon interposer. This is not the standard way today, because today's CMOS image sensor and then the backend processor are integrated on a package on the PCB, not on the interposer. But we propose that we can do that on interposer, because here shorter distance, which could save the data movement energy by 50 times if you do interposer-based integration compared to the PCB-based integration. So let's look at the thermal evaluation for the system. So assume this is a front-end CMOS image sensor with a two-tier design, as we discussed earlier. And then if you integrate that with silicon interposer, and then on top of the PCB organic package, then you have the backend FPGA for the detection and tracking. Then here you have 1 millimeter space between the two chips, and then the FPGA is very power hungry, so you have a fan on that. This is high-end FPGA. So you have pit spreader for the FPGA. But even with this kind of a power dissipation capability, then after we run the entire distance thermal simulation using the ANSYS software, then you see that FPGA here, if the FPGA is still hundreds watts, then the temperature will go as high as 85 degrees for the FPGA. And then this, because this is the CMOS image sensor is close to the FPGA, so this heat would penetrate through the silicon interposer to the CMOS image sensor. So the CMOS image sensor also has a high temperature, around 84 degrees C. So this thermal coupling is a big problem. So the FPGA 85 degrees C, that's fine. I mean, typically you can run the chip at as high as 85 degrees C. But the challenge for the CMOS image sensor is that if you have the high temperature, the photodiode dark current will increase. So your quality of the picture will become worse. So you do not want this high temperature to have that on the CMOS image sensor. This will decrease your image quality, like your contrast ratio, and so on. So then we have to have a solution for this high temperature. So FPGA is too power hungry for this backend object tracking and detection and tracking. So what we can do is to switch the FPGA to an ASIC chip for the backend processing. So as I said, FPGA is hungry, so it's better to design a specialized chip, low power chip. So here we are going to do a Vision transformer model for the object tracking. So we can develop some ASIC chiplet for the VIT, the Vision Transformer model. So then we can reevaluate the thermal profile after we design the ASIC for the backend processing. So here, a brief introduction to the Vision Transformer. So this is some state-of-the-art vision models. Typically for image classification, we have the ResNet kind of network, but here, take the advantage of the transformer. You can also do the vision transformer, which could achieve even better performance than the ResNet for many of the vision tasks. So here, the key module for the transformer model is this multi-head self-attention. If you recall the first paper for the transformer by Google, like 2017, the paper's title is "Attention is all you need." So this is the foundation for the transformer. And we'll talk about that more in a minute, because the transformer is the basis for today's ChatGPT as well, for the language processing. But here we apply this to vision, the image classification. So here then I skip the details, but let's look at the multi-head self-attention module. You still have the layer normalization and then the multi-layer perceptron fully connected layers in the transformer encoder. And then, but the most intensive computationally intensive module is this self-attention module. And then here you have many blocks. Here you have the input feature map, output feature map, and then you have a lot of matrix multiplication in this module. So you have the different quantity, like K, Q, V, and then you have the matrix multiplication between the K and Q, and then after soft map, you have the multiplication between the attention score and the V, and then you have a lot of matrix multiplication here. We need to accelerate this computation. So what we propose is the 3D stacked accelerator for the VIT. So we take advantage of our past RN, computing memory chip, and also the digital SRAM based digital SIM. So as proposed by TSMC. So here then we are going to address the compute operations into two categories. So first of all, the total model size for the vision transformer is about 28 megabytes. So this could be fully stored on RN, but the RN chip size, according to TSMC, each RN die maybe you can hold up to a few megabytes. But for the entire model, maybe you need 3 or 4 RN dies. So that's why we stack that vertically, assuming we have the bounding in between. And then for the compute, the matrix multiplication, there are two kinds of matrix multiplication. So for the linear layers with a trained parameter, then we can do the RN based analog computing memory, because here those weights are pre-trained. We don't need to, just inference. We don't need to retrain. So RN computing memory, and we can take advantage of the throughput in parallelism. But then for the attention score generation, we need to do the, so here basically we have those RN modules take care of those linear layers. And then for the dynamically operated attention score calculation, because here you see those modules input is after the computation of those linear layers. So that means the input is dynamic, or those inputs are generated at runtime. So you have to use SRAM to do that, because you have to write in the data. And therefore, SRAM, is easy to write. And then you can dynamically use the SRAM-based digital SIM to do this matrix multiplication. So you don't want to do this in RRAM, because RRAM write is very expensive. So for any intermediate data that you need to generate it on runtime, you don't want to write into RRAM, you want to write into SRAM. So that's why we have this heterogeneous design for the linear layers, because here the weights are predefined for the inference, so you can use RRAM. So anyway, so here the RRAM is designed in 40 nanometer because we have the PDK from TSMC, and then the peripheral circuits again, as we discussed earlier, we can use more advanced node if we don't have the high voltage. So here the tier 2 is a preferred circuits like ADC for those R1 dies. And finally, at the bottom, we have the 60 nanometer SRAM based digital SIM and other logic components to do the post processing, and then have the global buffer on the bottom die with SRAM cache as well. So this is the entire stack for the 3D Weixin transformer model. So here, let's skip this because we already addressed that. So ARM-based annual compute, this is the diagram. So same as tape out, we have this ARM with the ADC, and then shift and add, and so on. And then SRAM-based DCIM, this is the same as the TSMC's proposal. So have the SRAM and then the local low gate. So have the local multiply accumulate, and then have adder tree for that. So this is the same as TSMC's paper. So here then this is the evaluation setup. In total, we have 5 tiers, 5 dies stacked in this way. And then this die thickness, the bottom die. So here again, this is let's say the bottom die here is the silicon die with 100 micrometer thick. But for other dies, if you do the bonding, you have those thin the die. Basically shrink the thickness of the dies for the bonding. So you have to shrink that to 10 micrometer thick for each of those top dies. And then the total, let's say the package, and then package level, you have the heat spreader on the package. You still need to, running the fans with the airflow to cool the system. So this is a heat dissipation coefficient from the air fan. And then the hybrid bonding pad, and then the bump. So here at the bottom, you have the macro bump to the package. So then the bump dimension is 50 micrometer, and then the bonding pad is for the hybrid bonding is 3 micrometer. So this is a little bit more aggressive in assumption. And then here are some more parameters for the TSV. I will skip the details, but within the industry's capability. So many of those parameters are similar to AMD's 3D cache design. So here, if we compare the electrical performance between the two-dimensional 2D baseline, so everything is on 2D 14 nanometer process versus our hybrid 3D design. So the total footprint, of course, will be reduced significantly because we have 5 tiers folded. Then the total footprint will be much smaller. And even total silicon cost is smaller because here we have more advanced node. Instead of only 14 nanometer, we have 5 dies. But here the clock frequency will be a little bit lower because of the prosthetics. We have to pass the signal across the those TSV. So due to the prosthetics, the clock frequency will be a little bit lower. That's why the throughput will be a little bit lower than the 2D design. However, here the advantage is that the compute density is much higher because the footprint is much smaller, so we can have more compute density. But the overall energy efficiency is better because here we have the more advanced node, a digital SIM, and so the energy efficiency will be better. And also we evaluated the accuracy impact due to the prosthetics of the bonding pad. So the prosthetics capacitance and resistance, for example, the capacitance will only decrease the latency as I mentioned. So the clock, it will not really influence the computational accuracy. It will be a little bit slower, but then we can still have good accuracy. The resistance will impact the accuracy. However, the TSV's resistance is pretty small, hundreds of millions compared to the RM resistance. So then the accuracy will not be affected. This is negligible. So finally, for the thermal evaluation, so for the 5-tier design, if we do layer by layer computation, and we don't activate all the layers at one time, then the maximum temperature will be like 56 degrees Celsius. So which is reasonable for this kind of system. And so we think this is still feasible in terms of 5-tier design if we do not activate all the tiers at the same time. And if we can optimize the data flow to enable the layer by layer computation. However, if we do more aggressive pipeline design, activate 5 tiers at the same time, then the temperature will increase significantly. That will cause a lot of challenges in the 3D IC design if you activate the entire 3D stack. So this needs further solutions to address the thermal issue. All right, then next, we are going to discuss the LLM. So here, very briefly, the large language model, today very popular, ChatGPT. So we already have the ChatGPT 3 or even 4. So in terms of model parameters, the ChatGPT. So we started from the BERT model, which is the processor of the GPT. And so the BERT model is like 100 megabytes, and then GPT-1 is like close to gigabytes, and GPT-2 is like a few gigabytes, GPT-3 is 100 gigabytes, GPT-4 is like 1 terabyte. So the model parameters is very large compared to the image vision models, only a few megabytes, ResNet a few megabytes, 10 megabytes at most. So that means to address this large model size, this won't be single chip solution. You have to have multiple chiplets and a very large package for this. So here, then we propose, again, this is a transformer self-attention module, very similar like the vision transformer we discussed earlier. I will skip the details. But if you look at the matrix multiplication and types, here you have the dense matrix multiplication, dense matrix, but sparse output, and sparse matrix multiplication. So you have different characteristics for those matrix multiplication. So that's why we can use a heterogeneous architecture to accelerate those different types of multiplication. So here you see we have 3 candidates. One is the digital SIM, the digital systolic array, and then we have the SRAM-based analog computing memory, and then FE-FET-based computing memory. So they can deal with different layers. For example, here if we have the entire system like this, then each chiplet is a 3D stacked cube. Then for the FE-FET computing memory, it could be very useful for dense memory multiplication. This is like the R1 analog memory computing memory in the previous vision transformer model, because here FE-FET, of course, as we discussed before, is better than R1 in terms of the performance. So we switch from R1 to FE-FET for the analog computing memory for dense linear layers, because here the weights are pre-trained. We don't need to write into the FE-FET. So this is good. And also then the for this sparse matrix multiplication, then we can have the SRAM and for the computing memory, because we have to, again, this is to deal with this intermediate data, we have to use SRAM to write into the SRAM. And then finally, we can use the digital systolic array for some other computation. So here, this is like a 3D cube for heterogeneous compute models. But again, this is too small, one 3D cube for this large model. We have many of those cubes in the 2.5D silicon interposer. So this could be the heterogeneous platform for the futures transformer model, large transformer model. This transformer model is larger, much larger than the vision transformer we talked about earlier. For language, this is, gigabyte, tens of gigabyte, hundreds of gigabyte. For the vision transformer, it's only tens of megabytes. So a single 3D stack is good for the vision transformer. But this one, we need many of those 3D stack. So here are more details due to the time limit. I will skip that. So basically, as we said earlier, we're going to use this FE-FET-based computing memory to do the linear layer, the dense matrix multiplication, and then for the attention score, we have some strategies to use approximate computing for the attention score calculation. So basically, we're going to look at the MSB first. If the MSB are all zero, then we will just use a analog computing memory. But if we need high precision for the high magnitude, we are going to switch that to digital math because that could give us higher precision. So we'll skip the details of the algorithm customization. But I just want to quickly show the data flow for the 3D cube. So here, for example, the input token, and then first go through the linear layers on the top FE5 dice, and then pass those partial sum down to bottom, and then further down to the SRAM-based computing memory for the attention score calculation. If we need high precision, then go down to even to the digital systolic array for those high precision bits. So this is the input is going vertically down, and also the partial sum is also going vertically down. Sorry, the implementation map is actually moving up and then distributed to the blocks within each tier, but the partial sum is moving down. And then for the attention score calculation, then this is based on this high precision computation. Then it's based on the digital map with a systolic array. So I've skipped the details. This is a standard implementation of the systolic array, like the TPU. So I just want to say how we evaluate the system. So here we're going to customize our neural scene, but then we're going to integrate the interconnect models with the neural scene. So including the TSV and 2.5D link parasitics, we're going to get the interconnect energy and latency to transfer the data between the dies and between the cubes. And then we will get the PPA estimation from the neural scene and also systolic array like TPU simulator. So we can get the total energy and timing for the data flow. And then for the algorithm, we are going to partition the language model into different dies or different cubes, and then different tiers according to their characteristics. And more parameters for the setting. I've skipped the details, but here we have the heterogeneous configuration. As I said earlier, for the 3D cube, we have the FE5 dice, SRAM dice, and systolic array digital dice. So this is our optimal solution. But also you can have some homogeneous designs. For example, you can use all the SRAM for the 16 dice in total, 16 tiers in total. You have all SRAMs. So this will be homogeneous SRAM design. So this could be your baseline, but we have the optimal design, which is heterogeneous. And then those are the parameters for all the designs. I'll skip the details. For the SRAM FE5, those are design parameters. And here are the interconnect parameters for the bonding, TSV, and the silicon interposer. So what is important is here's energy and the bandwidth, I/O bandwidth for the TSV and bonding. So here, typically, you need a fraction of picojoule per bit to transfer the data, depending on, of course, those parameters. And then here, we are going to show the some validation of the interconnect model. So basically, what we have modeled is this TSV with those parasitics like diameter and the Q-pulse zone. So, and also here, this is a view, you look at the TSV array. And then the interconnect, basically on the interposer will be the wires, and we have to model the wires as RC distributed network. So you will have the parasitic RC. So basically, we can get the latency and energy to transfer the bit vertically and also horizontally, depending on the thickness and the distance between the cubes. So here, then this is the technology trends. If we stack more tiers, then of course we are going to save the area, but then the energy efficiency will be lower because of the parasitics moving the data vertically. And then here, if we increase the bandwidth or number of TSVs, then we're going to, of course, decrease the latency, improve the throughput, but then you are going to spend more area on the TSV because TSV is not cheap. Each TSV is a few micrometer, and then you have the keep out zone, and then you are going to spend more area. So those are obvious trade-off in the design. And then here we have evaluated the accuracy for the approximate computing we said earlier. So here we have evaluated the BERT-based model and GPT-2 model for the approximate computing for those attention score. If we drop some of this calculation, then we can still maintain some good accuracy for those F1 score, which is a metric for the accuracy. This is evaluated on those language models. And then for the hardware PPA, then here we have the normalized energy latency and silicon area. So here, of course, we want to know is the energy, know is the latency, and we have this homogeneous design, which is our optimal design as proposed here. So this is breakdown of the energy due to the TSV, MAC operation, computing memory, and so on. So here the silicon area, of course, will be a little bit higher than the homogeneous MAC operation, which is also SRAM, because those will be a purely advanced node. But here, we can get a better latency and energy due to the characteristics of this matrix multiplication that we have more optimized for. So this is a balanced design for the energy and latency. And also have to do some projection on the scaling. So if we scale, for example, the FEFET from 22 nanometer to 14 nanometer, then we are going to improve the TOPS per watt. And then also if we scale the bonding pad pitch for the 3D packaging scaling, then we are going to improve the TOPS per watt as well. But here, after certain generations, then the bonding's benefit will saturate. So really, to improve the system performance, we have to scale the technology node. So here you see that we have to switch the technology node from 22 to 14 if we want to further improve the density, the energy efficiency. Also here from the latency point of view, we can say that. So here the horizontal x-axis is just the packaging and scaling. So if we only scale the packaging pitch, then we can improve the latency a little bit. But if we want to really improve the latency, we have to really switch the technology node. So that means the packaging will help, but then still we need to scale the technology node for those memory technologies if we want to further boost the performance of the entire system. And finally, we will spend some time on the last topic, which is also a new topic. This is the bioinformatics for the genome sequencing. So some background for the genome sequencing. This is there is a workload called mass spectrometry. So basically, the basis for genome sequencing. So in the bio lab, you get all the wet experiments, and then you store the genome sequence into the database, and then for the future unknown samples, we are going to compare the genome to the existing or known genome database, and then do the matching and identify the variants for this, for example, the virus. So this matching process is done in dry lab, basically on computers. So the challenge here is that the genome sequencing, the data is booming. So for this database collected by UC San Diego, over 500 terabytes genome data for those viruses have been collected. So it's very difficult to match. If you have a new sample, you want to identify which variant of those sample belong to, then it will be a memory-intensive computation. So here are some algorithms to do those genome sequencing. I'll skip the details, but basically here what we want to do is to use hyperdimensional computing to accelerate those algorithms. We design hardware to support the hyperdimensional computing. So what is a hyperdimensional computing? Hyperdimensional computing is, here you have the raw data, and then you're going to encode the data to a long vector, maybe 1,000-bit vector. So you project the data into a high-dimensional space, and then you're going to compare after the clustering, and then you're going to compare the distance between the, let's say, your stored long vector versus your newly encoded long vector, and then you're going to get the shortest, let's say, the minimal distance between the stored data and then the new data. So here, what we are going to do is to propose a 3D NAND-based computing memory, or actually it's an in-memory search engine for the hyperdimensional computing. The reason we use 3D NAND is that because the database, as we just shown, that the genome sequence data is like terabytes. There's no other memory technology that you can store terabyte data. Because those data will be stored in SSD anyway. So we do not want to load the data to DRAM, to your processor, GPU or CPU, to do the processing. So current practice, is that those data is stored in SSD. So to the DRAM from DRAM to your processor. Then this loading will take a lot of latency and energy. So why not we do the processing directly on the DRAM? Directly on the 3D NAND. So we do not move the data. So this is a key idea that we want to do this hyperdimensional computing with the 3D NAND directly. So here, this is a hyperdimensional computing, as I said. So we need to encode the data to the non-vector, hypervector, and then we in the initial stage we store all the database into this associative memory database, and then in the new, if we have a new sample, then we're going to do this similarity check between the query vector and then the stored vector, and then we're going to compare which class it belongs to, or it is closest to. So this is the similarity check, and then there's algorithm to do the encoding of the data. I will skip the details. But basically, this is the sequence for the genome sequencing. I just show the animation. So you have this ATTC, the 4 types of the genome data, and then after the encoding, you are going to convert to a long vector. It's actually 1,000 bits. Here we only show 4 bits, but this will be 1,000 bits. And then the new data come in, and then you also do the encoding, and then you do the comparison between those two, and then get which one should this belong to. So here, then we're going to use 3D NAND to do that, because this data is pre-stored in the 3D NAND. The database is pretty stored. So here, then what we need to do is to modify the 3D NAND a little bit. Mostly we still use the commercial 3D NAND peripheral circuits. Only difference is that here at the end of the source NAND, we're going to add the ADC and then the comparator and then the logic to do the comparison. So here, for example, we store the database into the multiple screen selector SSL. And then here you see that different vectors are stored here in different SSL across the 3D NAND. And then the query vector will come from the bitmap. And bitmap, in the 3D NAND could be a very long vector. So bitmap could have like tens of thousands bitmaps in one block. So you can have a very long vector loading in parallel. So here, then this the query vector will activate the bitmap according to the voltage of, let's say, when you have the rated voltage, if 0, you do not have the rated voltage. Then those data will basically be matched with the with those vectors. So here, because here you see only when those two, the query vector and the stored data are both 1, then you will activate this string, and then you will get the string current. And in other case, then you will have the two matched data, and then you have activate two string currents. So then you will get more current this way. So then for different blocks, you have ADC to digitize the current. Then the largest current give you the highest score. So that means the most matched case. So then you are going to have the comparator to determine which one has the largest value. So this is the principle for this associative memory design with the 3D NAND. And then here, still the entire system will have more components just than the 3D NAND associative memory. So we still have that encoder because the raw data needs to be processed. And also we need to have the ADC and buffer and the input output and control. So those should be fabricated using a separate CMOS wafer. The reason is that 3D NAND has very limited logic process. So 3D NAND logic is very slow. So we have to design those logical circuitry using a separate CMOS wafer, and then we do the face-to-face bonding. And this is what we propose. So here we have evaluated the data set for this micro organism genome sequence data. And then also we have adopted the 3D NAND parameters from the industry publication and the digital circuit synthesized using 7nm ASAP PDK, and then integrate everything into the 3D the neural sim to do the evaluation. So here on the ADC precision, we figure out for this particular application, we only need the 4-bit ADC. And then even we have some distribution of the string current, we can use 4-bit ADC to achieve good accuracy for the data classification. And then also we have evaluated the sensitivity of the accuracy against, for example, the on-current distribution, or let's say the sigma of the on-current of the 3D NAND cell, and also the shift of the VTH of the 3D NAND cell. So it seems that we have some robustness, at least up to a certain level. So here the dashed line is what we get the parameter from this publication. So this is measured from the 3D NAND cell. So at least to the experimental level, then the accuracy is robust. And then in terms of performance, so here we have shown that, for example, if we do this for a single genome detection, we need to spend here, for example, overall, let's say the average energy will be like 16 millijoule, and then take us like 7 milliseconds to do that. So this is much better, let's say, than you load the data to the GPU, because even for the data loading, you are going to spend like 1,000 more energy. And here is a breakdown of the performance for the entire system. So here you see that most of the performance is dominated by the encoder, which is digital logic. We have to encode the raw data to the non-vector. So that means we have to further optimize the encoder design for the future optimization. So the 3D NAND is not the bottleneck. The bottleneck is this encoder circuitry. All right, so due to the time limit, I will quickly wrap up. So we talk about the Moronic 3D first, which rely on the background line transistor. And then the 3D EDA tool is possible but we need changes to some of the EDA tools to support the 3D IC design. And we also emphasize a lot on the 2.5D and 3D integration to enable new applications on the package level. beyond the the logic memory integration, we have other integrations available. For example, CMOS image sensor for smart camera, and for large models, for example, large language models, bioinformatics. Then we can take advantages for 3D DRAM or even 3D NAND, and also even 3D DRAM in the future. But still, again, for most of those 3D integration, the challenge is the thermal management and also power delivery. So those should be further optimized for the 3D integration. And here are a few publications if you want to dig into the details of the designs we mentioned today. But I think that's the end of today's presentation. We still have a few minutes to take some questions. Thank you.
谢谢于老师。那个各位同学和我们各位同仁，大家有没有一些问题想要跟于老师交流的？那个同学或者是师长们有问题的话，你们就可以直接打开麦克风，直接问就可以。
那于老师这边想跟您请教一下，就是您有一页投影片有讲到从 2.5D H3D 一直到现在的这个 monolithic 的 3D 这整个 trend， 那就发展上来讲，现在应该比较成熟是 2.5D 可能相对成熟一点。那就着您来看，对，就是在怎么讲，就是市场，就是说怎么讲，就是它这个商用的，就是各个技术环节，他们现在是大概是卡在哪一些点，以及您觉得大概这个它大概什么时间点哪几个技术可以再往前再 mature 一点呢？
对，现在比较成熟的 2.5D，比如说我刚才说GPU 对吧？这个就是台积，比如说 Coworks，那他拿这个他做NVIDIA 的 GPU，然后把比如说 Memory Company 的 Micron 或者是 SK 或者 Samsung 的 HBM 跟这个 GPU 一起做在 interposer 上面，这个技术都是比较成熟的。然后move forward， 如果是要做就是 Heterogeneous 3D， 但是我最近看报道也有说，这个下一步 NVIDIA 跟 SK Hynix 他们下一代的 GPU 要把这个 HBM 直接放在 GPU 的上面，而不是放在侧面。现在是 GPU 在这里，然后这个HBM 在这里。然后他们说下一代的 GPU， NVIDIA 和 SK 有一个合作，是 SK 还把这个 memory 放到上面去。但是最关键的问题有两个，一个是这个pitch scaling 还需要进一步，比如说你现在 micro bump 30个 micrometer square， 的 micro bump， get rid of micro bump， 你用这个hybrid bonding， hybrid bonding 像 SRAM 像 Vcache，AMD Vcache 也是用 hybrid bonding， 这些都是可以的，但是最大的问题现在是 thermal 还有 power delivery， 你怎么解决这个thermal issue？ 因为你这个现在这个在中间的 layer 的 thermal 是 heat 是比较难这个处理的，所以说现在大部分情况下是 memory on top of logic， 你很少看到 logic on top logic。The reason is memory 带还是温度和这个 power consumption 会低一些，所以它不会产生那么多的热。所以下一步你能看到的 application 是 memory on top of logic。但什么时候你能看到 logic on top of logic？ 有两个 GPU 带，你这样叠着，这个是比较困难的。现在这需要新的 thermal solution， 比如说他们有 liquid cooling， 或者说新的 thermal material 把 heat dissipate 出来。所以这些都是需要进一步的这个 co-optimization， 不仅仅是这个就是 chip design， 这需要整个 package level 的这个 solution。
OK， 谢谢。另外也刚刚好想请教一个问题，因为有看到您最后面在讲那个 3D NAND Flash， 那因为想请教说，好像 3D NAND Flash 应该不是第一天的事了，这应该已经一阵子了。 那只是感觉好像最近这个东西好像又被拿出来谈，就是想请教一下于老师，这个最近大家在谈这个3D NAND Flash 和这个2001年那个时候大家谈3D NAND Flash 那个时候，是有什么新的技术的进展？
没有这个 3D NAND，它本身是 monolithic 3D 的这个，比如现在200多层或者300多层的 3D NAND，这个技术是很成熟的。然后 industry 还会做更多的，比如512层，比如再等2年。这 3D NAND itself 它是 3D 这个没有问题。所以我们这里提到的 3D NAND 的 heterogeneous integration 不仅仅是 3D NAND，我们是讲 3D NAND 和 logic 的 bonding，因为 industry 现在他们做的只有这一块，只有这一部分。然后我们是说这个东西啊，加上这个 CMOS 的这个 wafer，然后做这个3D NAND 的 processing。所以现在 industry 他们有做的是下面这一块，这一块是可以做的，3D NAND 这200层、300层都是可以做的。然后我们是说在这上面再加一层 CMOS wafer，然后做这个 bonding，这个是 industry 现在做的比较少的。
OK，谢谢。
还有什么问题吗？
谢谢林老师啊，谢谢于老师。还有没有同仁有问题的？就是那个于老师您的那个 3D 的那个论文呢，我们先请看，就是说你除了用这个传统大家 3D 用的这个 TSV 以外，你已经有用就是它的这个 dimension 更这个更 compact 的这个就是 connection。那但是我们就是做 design 的人，我们有另外一个问题，就是说你就是把不同的制程整在一起的时候，那我们的那个 post layout simulation 的部分，我们这边会怎么样来执行？
这个要去问我的 collaborator Professor Sam Kulin，他们 group 是 specialized in 这个 3D EDA flow，他们可以做这个 post layout simulation for the entire 3D stack。具体是怎么做的，我不是很清楚，这个是要问他们 group，我跟他们有一些合作，但是
OK，
我们这边
但是
并没有
anyway 你们还是有 solution 可以让这样的事情的。
对，他们是需要 customize 一些这个interface between 这个 different tiers，但是它还是用的 commercial tool，还是 Synopsys 或者 Cadence 的 tool，但是你需要这个做一些调整，做一些调整，还做一些 custom coding。
OK，
这个
对，
首先你要不同
我知道
的这个
Cadence 有一些 tool 是就是特别 support 这个 for 3D IC 的，for 尤其是这个除了 single chip 以外的，他们都就是有非常就是我们以前在学校里面比较少用的一些 tool 啊。所以也是就是要 take 这边的 group 嘛。
对，我们这里浙江这个 group，他们有自己的这个 tool，他们也跟这个industry 有很多合作。
好啊，因为我们就是上次有跟于老师提到，我们原本是想说看暑假的时候有没有机会派几个优秀的学生去跟你们学习一下，但是我老板就吴老师他就是因为我们计划的需求啊，所以他更积极一点。他说寒假那边台大的学生可能就会先过去跟你们拜访，我可能就是他们过去学习了以后，我再跟他们请教好了。
好的，没问题。
谢谢。那个还有没有其他同学或者是老师们有问题想要一起提出来的？我们时间好像差不多了，就可能也许在最后一个问题，好不好？
最后还有什么问题？
有吗？各位同学，那个任新奇还是陈俊福？
那我问一个问题好了，就是 3D IC 其实在之前已经很久了，那它的温度就是一直因为它叠上去嘛，所以它的散热问题一直是它核心的问题。那我想问说，那如果像这样叠2层 process 以后，在上面再叠再叠 memory 这种，它每次 memory access 它电流要从上面流下来的话，那要怎么去？它温度不会散不掉吗？那导致它的性能可能会被降频或是怎么样？
对，如果你温度就是散不掉的话，那肯定会影响你的这些 clock frequency 啊这些。对。 但是memory 的话，我说了，一般来说比 logic 它们 power consumption 更低，所以你 stack 这个 memory 是 HBM，not too bad。核心的问题是 logic 和 logic，
好，那要怎么去分析说它的热会不会影响到它的效能这件事情？
你首先要做这个 thermal evaluation，我们就有一些 ANSYS 有些 tool 可以做这些，然后你 thermal temperature 拿到之后，那你根据 temperature，那你可以看你的这个是需要一个 code simulation，就是我们需要 power density，然后去产生这个 temperature 如果太高，那你就要改你的 clock frequency，你就会降 power，你重新 evaluate temperature，你可以做一个 loop。Temperature depends on 这个 power density，power density depends on 你的 power depends on CVDD square times F。
OK， 那个
谢谢老师。
对，那个俊福，你可能就是那个贴 tool 上，就是比较 advanced 的 tool 上，它应该都已经有至少 thermal 分析的这个功能在里面。就是你们如果有机会的时候，可以试着去 run 一下，就是对于于老师刚讲的东西就会比较有 sense。OK， 那因为时间的关系，我们就先到这边，好吧？非常感谢于老师。那因为实际上我们大家做的这个研究的关系啊，我们其实有很多问题，可能之后会再找机会跟于老师请教，好吧？那至少就是您帮我们透过这几次的介绍，我们就是对于一些background 的东西，或者是 advance 您这边研究的东西，我们就是在执行的学生们可能会比较有 sense。那我们其他的同仁就是有些老师或者是有些团队，他们对于这方面有兴趣的，他们也透过这个机会学习到一些经验。OK， 那我们最后再谢谢于老师，谢谢。
OK，谢谢。
谢谢。
好的，那再见。
好，谢谢，拜拜。
好的，拜拜。